Every idea in calculus, derivatives, integrals, continuity, all of it, is built on one concept, the limit. So before proving any more specific results, let's actually answer the basic question. What is a limit? Take a function, say f of x equals x squared, and pick a point, let's say a equals 2. The question is not what f does at 2. It's what f is heading toward as x closes in on 2. Watch what happens as x creeps up on 2 from below. 1.5. 1.9. 1.97. Notice f of x is doing the same thing, sneaking up on 4. We write that like this: the limit, as x approaches 2 from the left, of f of x, equals 4. That little minus sign on the 2 is doing real work. It means we only ever approach from below, we never actually land on 2. Now let's come back the other way, from above. 2.8. 2.1. 2.02. And f of x closes in on 4 again. So the limit as x approaches 2 from the right is also 4. Both one-sided limits agree. And that's exactly the condition we need. When the left and right approaches head for the same value, we drop the little sign and say the limit, plane and two-sided, as x approaches 2, equals 4. That's the whole intuition. As x gets arbitrarily close to a, f of x gets arbitrarily close to L, and it has to do the same thing from both sides. Now, gets close to is a nice phrase, but it isn't mathematics. Here's how it was made precise. Take a simpler function, f of x equals 2x. As x approaches 3, f obviously approaches 6. So a is 3 and L is 6. Now here's the game. You pick a tolerance around L, any tolerance, however tight, and call it epsilon. That's the yellow band. My job is to answer with a tolerance around a, call it delta, the blue band, narrow enough that any x inside it gets sent into your yellow band. For this function I can always do it, and I can even tell you how. 2x minus 6 is less than epsilon exactly when x minus 3 is less than epsilon over 2. So delta equals epsilon over 2. Whatever you pick, I have it, and I win. That's the definition. For every epsilon greater than 0, there exists a delta greater than 0, such that whenever x is within delta of a, but not equal to a, f of x is within epsilon of L. Watch what that means: shrink epsilon as much as you like, and a matching delta is always there. The bands close in on the point together, and they never fail. Now here's the twist this whole video is really about. Take f of x equals x squared minus 1, over x minus 1. Plug in x equals 1 directly, and you get 0 over 0, undefined. Full stop. But that's not the end of the story. Factor the top, x minus 1, times x plus 1, over x minus 1. For any x other than 1, those cancel, leaving just x plus 1. So the graph is a plain straight line, with a single point punched out of it, right at x equals 1. And the limit as x approaches 1 is 2, even though f of 1 doesn't exist at all. The limit only asks what happens near a point, and it doesn't care whether the function is even defined there. It gets stranger. What if we just define f of 1 ourselves, say, f of 1 equals 3? Doesn't matter. The limit doesn't move. It still only cares what happens near x equals 1, not what value, if any, sits exactly at that point. But hold on. We got 0 over 0, we did some algebra, and out came 2. So does 0 over 0 mean 2? Let's test that, because the answer matters more than almost anything else in calculus. Here are 3 fractions. Sine x over x. 1 minus cosine x, over x. And 1 minus cosine x, over x squared. Send x to 0 in any of them, and the top goes to 0 and the bottom goes to 0. Every single one is 0 over 0. Same shape, same collapse. Now watch the actual numbers as x closes in on 0. The first one settles on 1. The second one settles on 0. And the third settles on 1/2. Same 0 over 0, 3 completely different answers. And look at the last two, they have the identical numerator. Only the denominator changed, and the answer went from 0 to 1/2. So 0 over 0 can't be a number at all. It's what we call an indeterminate form. On its own, it tells you exactly nothing. What decides the answer is how fast the top and the bottom race each other to 0, and finding that out is precisely what taking a limit is for. Limits don't always exist, though. Here are three classic ways they fail. First, a jump. Approach 0 from the left and the function sits at -1. Approach from the right and it sits at +1. Both one-sided limits exist perfectly well, they just disagree. And since they disagree, there is no single two-sided limit. This is exactly the agreement condition from earlier, failing. Second, blowing up. 1 over x squared grows without bound as x approaches 0. We write that as the limit equals infinity, but be careful, that's shorthand for it grows past every bound you name. Infinity isn't a number the function is settling onto, so there's no finite limit here. Third, endless oscillation. Sine of 1 over x swings between -1 and +1, faster and faster, as x approaches 0. It doesn't jump to a wrong value, and it doesn't run off to infinity. It simply never settles on anything at all. So why build an entire course around this one idea? Because every derivative is a limit. F prime of x is the limit, as h goes to 0, of f of x plus h, minus f of x, all over h. Look closely at that fraction. Set h to 0 and the top becomes f of x minus f of x, which is 0, and the bottom is 0 too. It's 0 over 0, the indeterminate form we just met. Which means the slope of a curve is never something you get by plugging in. It's hiding in the race between the top and the bottom, and a limit is the only tool that gets it out. Limits also give us a precise definition of no gaps in a function. F is continuous at a exactly when the limit as x approaches a equals f of a itself, the limit and the function value finally agreeing. A limit describes what happens near a point, not necessarily at it. Once you really believe that one sentence, the rest of calculus starts to make a lot more sense.